Okay, just want to make sure everybody can see the slideshow. Example 6, indeterminate forms, blah, 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 right? That is on your screen, right? I assume that's a yes.
Yes.
All right, good deal. Thank you. Okay, I'm going to get this taskbar down as much out of the way as I can. Okay, I'll also scoot this thing over. Jonah, of course, is in the way, but we'll get that scooted over. And here was the example we started working on last time. Okay, so I think we'd better go to the white page. I'm sure we had started on this, but let's go again. Sure there's no issues that you want to bring up? Let me make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Before we get started today. All right. Let me get this taskbar out of the way. And then we'll almost be ready to go. What I'll do, the one last thing, is scoot the whiteboard over just a little bit so we'll have maximum room to write. Okay. If there are no questions, we'll get started on example 6. And by the way, I think I mentioned this before. If I didn't, I'm sorry. I wish I had. You can go to larsoncalculus.com for an interactive version of this type of an example. And here's what we're looking to do here. We're looking to find the limit as x goes to 0 from the positive side this is pretty ugly writing. X goes to 0 from the positive side of sine x raised to the x. That's not a very pretty x up there, but it is one. Now, I heard some static with someone trying to get in to say something. Okay. Now, I really regret that I wrote it like that because I should have left room on the left to write. The first thing to do to find that is the sum. Well, let's just call that y. That's what we're looking for, y. Okay, here comes somebody, and I can't see. Oh, I think it's Kyle. Okay, so let me get Kyle present and accounted for. Okay, got Kyle here. Has anyone seen anyone else show up? And I don't know if you can see this box down here. Please move this window away from the shared application. It won't budge. So they say that, but what it does, when someone comes in, they try to cover the name. Okay? So I moved the window down as far as I can. It's still, now it's going to do this the rest of the day. And in Monday afternoon's class, I had a guy who came to get into class after he got off work, and he said he could never get out of the waiting room. And the only thing I can figure is this thing has started doing this, and once it does it, it just keeps doing it, so I don't really notice it anymore. And evidently his name was behind it one time, but I couldn't see that because it blacked him out. And I don't know how long he stayed there. I can't believe I kept missing it, but maybe as long as he was there, it stayed dark. So please, if you sense that any of your classmates are trying to get in, please let me know so I can let them in, because this thing will block me from seeing them if it can do it. Okay? So that's sad enough. All right. Here's the first step. Let's just name that y. That's what we're looking for. Remember that. We're looking for y. So, first thing we're going to do, and I'm going to swap sides now, because this is something, a power raised to a power, the standard technique for clearing that, take the log of both sides. See, a log undoes an exponential, and that's exactly what we have here as an exponential. So I'm going to reverse sides, and the next step is to say, take the log of y. Remember, we're not interested in log of y, we're interested in y, but we'll get to that later. Now that's going to be the log of the left-hand side. Now we've moved it over to the right. Here comes somebody else. I can't see who it is because it blocked them. But let's see, who was that? I tried to catch it. Was it Esther? I believe it was. If I saw something, I thought I glimpsed Esther. Did anyone see Esther come in? Or trying to come in?
I'm here.
Okay, that's Esther? Great, thank you.
Yes, sir.
All right. The box down here on my page blocks your name, so I can't tell who it is coming in. And like I was telling the class, that happened evidently Monday afternoon in the class after this one, and I never saw the guy's name. I never saw that he was even trying to come in. And he said he was, and I felt so bad because we did a lab and everything. And see, this window just keeps showing up even though there's nobody behind it. So after a while, you start ignoring it. But there could be somebody behind it. So I'll try to keep an eye on that. All right, what we're saying, we took a log of what was the right-hand side. We moved it over to the left. Now let's take a log of the left-hand side up here, which we've now moved to the right here. Well, the log and the limit, they don't really relate to each other very much, so we can reverse the order. So I'm going to move the limit to the outside because I don't like to write any more than I have to. This will give us the limit as x approaches 0 from the positive side. Oops, here's somebody else. This time I see it, Daniel Thaxton. I saw it right when it came up before it blocked him out. So Daniel's here. Okay. Oh, I marked him in, but I forgot to let him in. Okay. Well, he'll be glad to know he was marked here even though he can't get in. Okay, hopefully he'll be here soon. X is approaching 0 from the right-hand side, from the positive side. And we reverse the order of doing it, so we're going to do the log in here. The log of sine x raised to the x power. Okay. Got to keep an eye on that thing. All right. Now, the reason we did a log, there are some rules for logarithms. And does anyone remember what the rule is where you're taking the log of a base raised to a power? Hopefully someone remembers that. And y'all are very much too shy to say anything, so I'll go on and tell you. That's the limit. I wish I didn't have to keep writing this. It's difficult enough to do. Limit as x is going to 0 from the right-hand side, from the positive side, the upper side. Okay, the log of anything raised to a power is the power times the log of that thing. Okay? One of the properties or principles of logarithms. Okay? So that's going to be the limit of x times the log of sine x. I guess I probably should put it in parentheses again so it doesn't run together like it was. All right. Now, what we've just done is changed it from as x is going to 0, as x goes to 0, sine x is also going to 0. And as x goes to 0, of course, x is going to 0. So this is a 0 to the 0th power. That's a not undefined thing. Any other number in the world to the 0th power is 1, but you have no clue of what something of 0 going to the 0th power is. On the one hand, you say it have to be 0 because there's nothing there to begin with, and raising any power, how can you get anything out of it? But on the other hand, anything raised to the 0th power is 1. Even an incredibly small number like 0.0000000001 raised to the 0th power is still 1. So who wins here? The 0 in the base or the 0 in the exponent? Okay? We don't know. Okay? Well, by doing this log transformation, what we now have is a limit of something as x is going to 0. This, of course, is going to 0. And if x is going to 0, of course, x going to 0 here, sine x would be going to 0. But log of 0 is not defined. Okay? Now, again, that's why it's a limit. It's not actually equal to 0, but it's going towards 0. But what happens to a log function as it gets close to 0? It gets more and more and more and more negative. So now what we have is something going to 0 here and something going to negative infinity there. But now it's a multiplication problem, not a power problem. But still, who wins? Okay? Usually anything multiplied by 0 is 0, but then negative infinity is an awfully big number, negative number. So who wins? Which one wins? Not at all clear. Okay? Now, here's the trick that they use next. We're going to rewrite this x as 1 over x, okay? Now, you tell me if that's a legitimate move. Here's your x, and we're going to say this is the same as 1 divided by 1 over x. Does anyone have any objection to that? What does this mean? 1 divided by 1 over x. You could write that as, I hate to do this, but I will, 1 divided by, write it this way, 1 over x. And now you have to go back to grammar school and remember how you divide fractional forms. You invert and multiply, right? You keep the first number the same, 1, change the division to a multiplication. Now that's, I shouldn't use a time sign, should I? Let's use a dot, center dot. Okay. Get back to my draw mode. 1 times, can you see the time sign? X over 1. And sure enough, that's x. All right? So what we've done now is change this x in the numerator to a 1 over x in the denominator. Okay? So that gives us the limit. I'm tired of writing it, but I'll keep writing. The limit as x is going to 0 from the positive side, okay, of, now it's going to be log of sine x in the numerator it's a pretty ugly s, isn't it? That's in the numerator, and that's an x there. That's a pretty ugly x. Okay? Over, and remember we changed the x to a 1 over 1 over x, so this will be over 1 over x. Okay, now how did that change anything? Well, this numerator, as x is going to 0, plus side, minus side, doesn't matter, x going to 0, this is going to 0. Oh, I said it didn't matter. If x were going to 0 from the negative side, sine x to the left of 0 is negative. You cannot take the log of a negative number. So that's why you have to be approaching from the right. Okay. But still, you can't take the log of 0 either, and sine of 0 is 0. So that's going to negative infinity. As you get closer and closer to 0 from the right, it's still going to negative infinity. What's this doing? This is 1 over 0. Well, that's going to positive infinity. Okay? So you have an infinity over infinity situation. That kind of situation, you can use L'Hopital's rule. Okay, so what we're going to, does anyone remember what L'Hopital's rule was? I'll write this one more time. Hopefully I'll soon will not have to. The limit as x approaches 0 from the right, from the upper side, from the positive side. L'Hopital's rule says take the derivative of the numerator and the derivative of the denominator. If they both exist, then you'll have the it'll have the same limit as the ratio of the functions. Okay. So what is the limit? What is the derivative of log of sine u? No, sine x. I can't read my own writing. Okay. Anyone remember what the derivative of log is? That's going to be a 1 over sine x. Okay? That's the first part anyway. Derivative of log of u is 1 over u, right? Except then it's multiplied by chain rule du. Well, the inner thing here, the u here, is sine x. And what's the derivative of sine x? Whoop, here comes somebody. I can't see who it is. It's Anita, I think. Did y'all catch the name? You probably can't even see the name. I think Anita Craig just came in, didn't she? Anybody? Can you see her yet? Is that Anita?
I'm here. You said yes.
Okay, good. It's Anita. Good. All right. We're doing the example 6 on page 350, chapter 5, integration, 5.6, indeterminate forms, and L'Hopital's rule. We're smack in the middle of example 6, which is using L'Hopital's rule. We finally got it into a form that L'Hopital rule apply. Okay? So, we had just started taking the derivative of the numerator. Derivative of log of u is du. Derivative of log of u is 1 over u, then times du. Well, du here, u is your sine. What is the derivative of sine x? Anybody? Derivative of sine x is? Please say you know, otherwise I've got to call your trig instructor. Okay. Derivative of sine u is cosine u. And Jonah, I know who your trig instructor was. He's going to be in serious trouble. Okay. Whoops. That was me. Okay. All right. So the derivative of log of sine u is cosine x over sine x. Okay? Now, what is the derivative of 1 over x? I like to think of that as x to the minus 1. Okay? Well, x to the minus 1, derivative of that is minus x to the minus 2. So that would be a minus 1 over x squared. Now, frankly, folks, this doesn't seem to have helped us much, does it? That numerator is, another way to say it, is cotangent x. Okay? And cotangent x, if you recall, starts from 0 at positive infinity, or going toward positive infinity, the y-axis is a vertical asymptote, comes down and at pi halves goes to 0, because at pi halves sine is 1 and cosine is 0, so that would be 0. And then it goes down to, at pi is approaching negative infinity. So as x is approaching 0 from the left, you're going to positive infinity. In your denominator, whoops, I left off the square. Y'all let me get away with that, didn't you? You need to be paying more attention. I make lots of errors. Don't let me, okay? So your denominator is x going to 0 from the right-hand side. X squared is also going to 0 from the right-hand side. And 1 over x squared is going to an infinity really fast, but you're negative, so it's a negative infinity. So whereas up here we had negative infinity over positive infinity, here we have positive infinity over negative infinity. And we still don't know where this is heading. Okay? Now, however, they're going to do another trick on us. Okay? Now, as I said, I'm not going to rewrite everything because it's so incredibly tedious. This is cotangent of x, right? That's what we just said it was. Okay? And this is 1 over, a negative 1 over x squared. Well, cotangent x, oh goodness, I didn't have my button pressed at all, and yet it drew a line. So let me see if I can get rid of that line. Okay. Now, cotangent x, as you see here, is 1 over tangent x. So you have a reciprocal up here, 1 over tangent x. Down here you have a minus 1 over x squared. Let's flip both of them, okay? Just like we did our division before, this time we'd have 1 over tangent over negative 1 over x squared. That would be negative 1 over tangent. No, I'm sorry, 1 over tangent divided by negative 1 over x squared. That would be 1 over tangent times negative x squared over 1. Well, that would just give you minus x squared over tangent x. So let's rewrite it that way. Now, that was a lot of verbiage. Did everyone follow what I was saying? That's the limit as x is going to 0 from the positive direction, the right-hand side, the upper side, of, now the new form I just said was minus, I'm going to just put the minus in front so I don't have to fiddle with it anymore, x squared over tangent x. Now, was that just mystery meat, or did someone follow how we got there? Did anyone disagree that that is a potential way to get there? All right. Now, let's see what we've got now. Now, that is a minus sign. It's not a very dominant. Oh, wait, here comes somebody else. I can't see who it is. Jalen. Jalen Maddox is coming in. Has anyone else tried to get in that you've been able to see? Okay. That should be 13 now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So evidently we lost somebody. Hopefully they're coming back. Okay. So you see what we did? We basically flipped numerator and denominator as we took the reciprocals of each of them, and that gave us minus x squared in the numerator and tangent x in the denominator. Whereas x is going to 0 from the right-hand side, of course x squared is going to 0 from the right-hand side, and tangent x is going to 0 from the right-hand side, okay? Because tangent of 0 is 0, okay? So we still have a L'Hopital form. Let's see if we can take another derivative, numerator and denominator. How many has this been now? I'm giving up, okay? Had a lot of changes. So again, this limit, pretty ugly M there, isn't it? As x approaches 0 from the right-hand side, the plus side, of minus, and let's take the derivative of the numerator. Anyone know what that is? Derivative of x squared? Please say yes. 2x. How about the denominator? What's the derivative of tangent x? Got to get in touch with those trig teachers again. That's secant squared x. SEC, that's not the Southeastern Conference. Secant squared x. I hope you remember that. Okay, derivative of tangent x is secant x. All right, can we finally, oops, here comes somebody else. Let's see who this is if we can. Could you see that? It flashed and then went away. Who was it just coming in? Help me, somebody. Who just came in the class?
Onesimus.
Onesimus. Oh, okay. So you were already here. You got kicked out or something, huh? You were talking in class and I kicked you out. No, I'm just kidding. Okay. All right. All right. Here's where we've gotten in the problem now. The limit as x approaches 0 from the right-hand side of a minus 2x over secant squared x. Well, as x goes to 0 from either side, this is going to 0. 2x is going to 0. The denominator, however, secant squared x, remember secant x is never 0. And as you're approaching 0 from the right-hand side, it's approaching 1. Because secant is 1 over cosine. And cosine of x equals 0 is 1, so secant is also 1. And 1 squared is 1. So we finally got our answer here. And it doesn't matter about the minus sign. This is 0. All that for nothing, huh? But sure enough, that is the limit. Because you got a 0 over 1, or negative 0 over 1. Who cares? Negative 0, positive 0, it's still 0. Okay? Any questions on that? Now, we're not through though. If you remember, this was all log y. So log y is equal to 0. That's all this is telling us. Now we've still got to figure out what in the world is y. Where is log y equals 0? Or is it ever equal to 0? Anybody? When x is equal to 1. So therefore, y, if you exponentiate both sides, e to the 0 is e to the log y, or e and logs are inverse operations. That's going to give you a y on this side, and e to the 0 is 1. So the limit of this thing equal y would then be 1. Y would equal 1. So that is your conclusion here. Now, I hope both of you have books. Some of you may have different books, so you can't see this. If you go to larsoncalculus.com, you'll probably see this worked out incredibly detailed, okay? And they do show, under technology at the bottom, a graphical display of what sine x raised to the x looks like, and that's it. Okay? And sure enough, as x approaches 0 from the left-hand side, the positive side, the right-hand side, the positive side, the y is approaching 1. And there's the graph. I never would have guessed the graph looked like that, but that's what it looks like for various values of x. All right. And like I said, if you want to see more detail, please go to larsoncalculus.com. You don't need a key code. You don't need any kind of code, a password, nothing else. It's just a website. Go to the website. Now, you have to figure out how to navigate it, but you probably can handle that too. All right, I think we're ready for example. Oh, wait, no. Let's go back to the text. Okay, we should have 14 people here now. What have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah. Okay, let's go back to the text, 5.6, where we left off. From current slide, this doesn't look like the current. Yeah, it does. Okay. And let's see how they did it. I think it's going to be pretty similar. Because direct substitution produces an indeterminate form, 0 raised to the 0th power, have no clue what that is. So began to assume that the limit does exist. It may not, but assume that. And if it is, set it equal to some value. They chose y, so we used y. It still doesn't help you know what it is, but just remember, that's what we're looking for, y, not any other form. We're looking for y. So the first thing we do to that, because we have a variable in a base and the variable in an exponent, log is the trick. So take the log of this side and the log of this side. Okay, take the natural log of both sides. Now, I didn't write that one down because I was already writing too much and it was too slow. But then the next observation is it doesn't matter which order you do it. So take the limit of the log, that's continuity, they say is the reason you can do that, rather than taking the log of the limit. All right? That still doesn't give you anything that's all that useful until you notice that a log of a base raised to an exponent is the same as the exponent times the log of the base, which gives you the next step, which is right here. And remember, this is log y we're talking about, okay? Remember that, that's log y, okay? And you've taken the exponent, moved it down here, and gotten this kind of an identity. Well, what's the limit of that as x approaches 0? That's going to 0, that's going to x going to 0, sine x is going to 0, but as the argument of log goes to 0, the log goes to negative infinity. So that's an indeterminate form. We don't know who's winning that battle, okay? So then they use that trick that we mentioned, rewriting x as 1 over x, okay? And we showed that was exactly true. Now see what we got. Well, you still got a negative infinity here. The log of something going to 0 is going to be very much a negative infinity. And down here you've got a positive infinity. If I could get my cursor to come back. There it is. 1 over 0 is going to positive infinity. So you still got an infinity over infinity, but at least this is one that's applicable to L'Hopital's rule. So we're going to do that. Take L'Hopital's rule of this, take the derivative of the numerator, and they skip some steps here. That's 1 over sine times the derivative of sine. Well, derivative of sine is cosine, and cosine over sine is indeed cotangent. Or 1 over tangent, you could have said, but you didn't know you were going that way. Whereas the derivative of 1 over x, which is x to the minus 1, the derivative of that would be minus 1 times x to the minus 2, which gives you negative 1 over x squared. Now you take the limit of that as x approaches 0. Cotangent is going to positive infinity as x goes to 0 from the right, and 1 over x squared is going to positive infinity, but it's a negative 1 over x squared. So that's going to negative infinity. So we've just changed the signs here into a positive infinity over a negative infinity. That's still not very helpful. Okay? But time for another trick. And this trick is rewrite the cotangent as 1 over tangent and then flip them. And you see they do it all at once. This is 1 over tangent divided by negative 1 over x squared. That would be times x squared over 1. So that would be a negative x squared over a tangent x. Okay? Again, an indeterminate form, but this time it's a 0 over 0 form. So at least it feels like it's getting closer to maybe being worked by L'Hopital's rule. So let's do it again. Take the derivative of this, you get minus 2x. Derivative of this, you get secant squared x. And that's what they get here. Minus 2x divided by secant squared x. All right. Let's take the limit as x goes to 0 there. Numerator, certainly going to 0. The denominator, certainly not going to 0 because secant never is 0. Secant, the minimum secant value is a plus 1. The maximum secant value, the minimum of a secant when it's above the x-axis is plus 1. The maximum of a secant when it's negative is minus 1. Well, as you approach 0, that's on the plus 1. So what you have here is a 0, negative 0 over 1. Guess what, folks? That's going to be 0. So that limit is 0. But remember what I told you? Remember this is log y, not y. So your answer is not 0. It's log y is equal to 0. Well, log y is equal to 0, you can conclude that y, if you take the exponential of both sides, excuse me, I'm having trouble breathing. I'm still sort of stopped up from the weekend. So see if I can loosen the head a little bit. I don't know if that works, but it tastes good. All right. So if you take the exponential of this side, e of log y is just simply y. Take the exponential of this, e to the 0, like any number to the 0, except 0, of course, is 1, except we've just seen that in this case, when your form is sine x raised to the x, that's in the form of 0 raised to the 0th power, that is indeed 1. Now, you can't say that for any form that's 0 raised to the 0th, but it is this one. And here may be a little bit of the reason for it. If you think of sine, when it's approaching 0, it's approaching almost in a linear fashion, okay? Because when you're real close to 0, positive or minus side of 0, that sine function is almost your identity function. I mean, it's very close to that. Okay? And then that number, all those numbers raised to the 0th power, they would have values of 1. And since it wasn't something that's hanging around near 0 long, which would be fairly undefined, but coming down pretty straight, this is just speculating here, that does indeed equal 1. Okay. And here's example 7. Oh boy, they got carried away here, didn't they? What's the limit as x approaches 1 this time? Oh, here's somebody else coming in. Let's see who it is, if we can catch it. Morgan. Okay, Morgan's iPhone's trying to come in anyway. I think Morgan was already here, wasn't she? Yeah. So she must have got kicked out and had to come back. Or had to go out and come back or whatever. Okay, so I think we've still got the same number of people here. As x approaches 1 from the positive side, log of x is 0. So this is a 1 over 0. Undefined, folks. Minus 1 over 1 minus 1. It's also 0. So you have a undefined minus undefined. Okay? Which undefined is going to win here to give it an actual value, or does neither one of them? Okay? And that undefinedness is positive infinity, by the way, because this is approaching 0 from the right-hand side, so 1 over 0 is a very large number, meaning positive infinity, and this is approaching 0 from the positive side. Because you're slightly greater than 1 and subtracting 1 from it, you're positive, so 1 over x here is positive infinity. So this is a form like infinity of positive infinity minus positive infinity. That's what the form is here. So do y'all want to see it on the white screen, whiteboard? Or would you just want to follow the book? Think before you said you wanted whiteboard, so unless you changed your mind, I'll go to whiteboard. So let me know. Say, hey, we don't need that anymore. I'll be glad to stop. Okay? So let's try doing this. Okay. Here's our problem. The limit, I don't have it in front of me anymore. The limit as x is approaching 1, I'm pretty much remembering that's from the right-hand side, from the positive side, of, and this expression was 1 over log x, minus 1 over x minus 1. Okay. Believe that's what it is. All right. Now, usually the first thing that comes to my mind when I see something like this is, let's get this thing, because if you remember, L'Hopital's rule, that's what we're studying now. L'Hopital's rule deals with something over something. Usually 0 over 0, which is indeterminate, though it can be an infinity positive or negative over another infinity positive or negative. So it could be something like that. This is definitely a subtraction problem. So if you got this over least common denominators, combine that, you're going to get a ratio. So that, to me, would be the first step, and indeed, that's what they do. Okay. Now, this goes back to, I guess, basic algebra, you would call it. No common factors between log x and x minus 1. So your common denominator is, I'm not going to write the limit sign. This is just dealing with what's in parentheses. Your common denominator here is x minus 1 times log x. Okay. Now your first numerator here, it's supposed to be an x. It's getting uglier and uglier. Okay. Now, your first numerator here was a 1, but that was just over log x. If you're multiplying that log x by an x minus 1, you must multiply the numerator by an x minus 1. So that gives you an x minus 1 here in the numerator. Okay? Now, then you have a minus sign. Now this denominator, x minus 1, you had a 1 over it. If you multiply that denominator by log x, you multiply the numerator by log x as well. So that's minus a log x. Okay. Did someone start trying to come into class? Something moved down here, but I don't see anybody there. Excuse me. Okay. Now, let's pause a moment here and try to reassess. Now, I left off my limit. Still, things are going to 1 from the positive side. So your numerator is something slightly greater than 1 minus 1. So that's really close to 0, but still positive. Minus something slightly greater than 0, but slightly positive. So basically, you're still approaching 0 from the right. Down here, you're 0 from the right times 0 from the right is still approaching 0 from the right. Okay, so you're still a 0 over 0 form. Now, is this any easier? Now, with the limit here, as x is approaching 1, you see this is something you can do L'Hopital's rule on. So I sort of wish I had written the limit there. I'll do it now. The limit as x approaches 1 from the positive side okay. Now we'll take a derivative. What's the derivative of x? Anybody? Need to talk with your Cal 1 instructor. 1. Derivative of 1? 0. That's a constant. And what's the derivative of log x? You got a minus sign there. That's 1 over x. Okay, does everybody agree with that? Now, the denominator is a little messier because this is a product rule. But it's not super bad. So how do you like to do product rule? First times derivative of the second plus second times derivative of the first. Okay with you? So the first is x minus 1. Times the derivative of the second, and that's 1 over x. So that'll be x minus 1 over x. Plus the second, which is a log x, times the derivative of the first. Derivative of the first is just 1. So that's just plus log x. Okay, so there's your denominator. Like I said, a little messier than the numerator was, but still there. Okay, so what do we have now? What's the limit as x approaches 1 from the positive side? Well, this is a 1, and this is a minus 1 over 1 from the positive side, but that's still approaching 1. 1 minus 1, 0. Nothing's changed there. How about here? X minus 1 is approaching 0 over 1. That's 0 plus log of x is still 0. So we still got a 0 over 0. Okay? However, you can fiddle with this a little bit. Let me make sure my fiddle is going to be the same as their fiddle. I think so. Okay? So here's what we're going to do. Still going to take a limit. As x approaches 1. From the positive side, okay, and what you have here, let's put this over x, sort of like we did before. Common denominator is x, Your first numerator was a 1 over 1. To get that over x, that means x over x. So that's going to be an x. And I'm creeping up the page. I'm running out of page to write on. Minus 1. So there's your new numerator. Let's do the same thing down here. Denominator is going to be x. Going to be a bigger mess down here, but we can still handle it. The numerator is still, for the first part, is still x minus 1. And the numerator for the denominator is going to be x times log x. So that's plus x times log x. Does everybody see the magic I'm doing there? It's not really magic, it's just algebra. Okay? All right. Now, here's something you can certainly do. Pretend you're inverting and multiplying this denominator, then these x's are going to go out because they will divide away, which is fine. They're both ones, not much of anything there. So what your new limit looks like is this. The limit as x approaches 1, I get so tired of writing this, from the positive side of x minus 1, guess what? It's still a 0, isn't it? Okay. Over x minus 1 plus x times log x. Okay. Whoa! Ugly, ugly, ugly. Okay. That's all a dividing line. Let me see if I can clean this up just a little bit. Well, guess what? Eraser's not picking up anymore, so you're going to have to live with it. I don't know why it goes so long and then won't do that. Okay? No one has any insights or guesses of how to overcome that? All right. Well, let's take our limit again. As I said, the numerator is still going to be a 0. The denominator, this part will be a 0, plus 1 times log x. Log 1 is still 0. So, yep, we're still 0 over 0. So let's try L'Hopital's rule again. Getting kind of tired of it, but this time I think we have promise. The limit, I'm certainly getting tired of writing this, as x approaches 1 from the positive side of derivative of x is 1. Derivative of 0 is 0. 1 is 0. Down here, derivative of x is 1. Derivative of minus 1 is 0. Plus, okay, another product rule. First times derivative of the second. Well, the first is an x. And derivative of log x is 1 over x. Ha! That's going to be a 1. Okay? Plus, second part of the product rule is the second log x times derivative of the first, derivative of x is 1. Okay? Okay, folks, what do we have now? We have somebody trying to come in. Can we see who it is? I think it's Joy. It seemed like I caught that. Joy Robinson. Is that Joy Robinson coming into the class right now? Who's sitting by the door and can tell? Okay? Never mind. Okay. I think it's Joy. All right, now let's take our limit again. We've been unsuccessful so far. Limit of that numerator as x approaches 1 is just 1 because there is no x in it. Of the denominator, it's 1 over 1, which is 1. So 1 plus 1 is 2, plus log 1 is 0. So guess what our limit is? 1/2. 1 over 2. Now, if you recall, we didn't take any logs or anything else here, so we don't have to go back and change a thing. This answer is 1/2. And fortunately, that's what the book got. Are there any questions on that? I'm sorry that writing like this takes forever, but do you see how we got there? Let's go back to the book, if I can find, or to the PowerPoint. And we'll go back to the PowerPoint for 5, 6, and see how they did example 7. Okay? Well, they started the same way we did. Okay? See if this will work. Yeah. Because, oh, here's someone coming in, and I can't see who it is. Can y'all tell? iPhone. Okay. Whose iPhone? See if I can recall. Who is? Whose iPhone? Was that James Mullins?
Yes, sir.
Okay, good. I knew you had been iPhone in the past, so I figured it might be you again.
Yes, sir.
All right, good deal. So James is here. Excellent attendance, folks. We're only missing Houston, Amina, and Laurent. Now, I don't know what's happened to Angelica. She never showed up, so I assume she decided not to take the course this summer. Now, time out for just a moment here before we continue with example 7. I can't remember if it was this class or not. It seems like it was. Someone asked Monday when the last day to pay was, it seems like. And I did not know. I still don't know. However, I have found this out. We do things strangely here at Lawson. And sometime after, so far into the term, they ask us to report anybody who has never shown up for class. Now, when they're interested in people who have never shown up for class, they mean paid students who never showed up for class. Okay? This class didn't have any. Everyone who paid showed up. A few people who haven't paid have been coming. One person who hadn't paid never came. That's why I assume she's probably not coming. Now, there's really no correlation here, but from my memory, and this is just going from memory, it seems like to me that usually shortly after they handle the no-shows, then they go through and purge the non-payers. Now, how much time that's going to take, I don't know. This summer is a weird summer because not only are we virtual campusing and that kind of stuff, we're also changing to a brand new course management system. Starting in the fall, but it actually has already started. The administrators have been going through training for months now, and we start training next week. That's department chairs. And then I think all faculty members start training the 1st of July. So, and before the end of July, everything has to be converted. Okay, and that's why, if you haven't noticed it, they shortened our summer term. We used to go till the first week in August. Now final exams have been moved up to sometime the last week in July. Now, it's only about a week's loss, but that's sort of significant for you guys, especially since we're still in Chapter 5, which you should have done in Cal 1, but because Cal 1 was messed up with the virtual campus type deal and all the problems that came with the, electronic versions and technology relying on that and everything that screwed up last spring. At least for me it did. I had a computer die twice, internet go out once. It's hard to teach an online course or a virtual class if you have a computer that's dead, or if you have, and this is at separate times, your internet goes out. And students were having the same problems, okay? So, we got behind, we're still behind, and now they're going to end summer early. So you folks going back to your parent campuses, I hope we don't shortchange you too badly. We'll try to get as much done as possible. But anyway, let's go back to what we're doing. And by the way, James, we're in Chapter 5, Integration 5.6, Indeterminate Forms, in L'Hopital's Rule. We're on Example 7 on page 351. I think you probably do have a book because you're a Lawson student, so I'm assuming you have this text. Okay, so here's what we got. And now that I think about it, yeah, your Cal 1, we were still using the old book. So you may have the old one. If you can't find it where it was, it's the same authors, but they just rearranged the chapters. Find it in the chapter. Most of them are very similar. Okay, so direct substitution yields an indeterminate form of infinity minus infinity. We talked about that. So to try to rewrite the expression and produce a form, you can apply L'Hopital's rule. L'Hopital's rule is a ratio, numerator over denominator. So let's combine these two fractions into a single fraction with a least common denominator. Least common denominator being the product of these two, x minus 1 times log x. The new numerator for the first one is going to be an x minus 1. For the second one, a minus log x. I know it's going behind the box now, but it'll come out in a minute. Maybe more than a minute. But it will fade away sometime. It won't stay away long, but it will fade away. Go on and get out of there. There it goes. So here's our new limit. Now that's a form that maybe we can use L'Hopital's rule. As x approaching 1, this is 1 minus 1 is 0, minus log 1 is 0, over 1 minus 1 is 0 times 0. Yes, we can use L'Hopital's rule. For the first time. But now I can't get the slide to advance. Now, okay. Now, because direct substitution produces an indeterminate form of 0 over 0, you can apply L'Hopital's rule. Okay? And when you do that, derivative, and they actually took a step and wrote derivatives of each of these. I don't know why. You could just take a derivative of the first and the second. So let's get on to that slide. And that would be derivative of x is 1, derivative of minus 1 is 0, derivative of negative log x would be negative 1 over x. And down here you have a product rule, so it's the first times derivative of the second, so it's x minus 1 times 1 over x plus the second log x times the root of the first. Derivative of x is 1. Negative 1 is 0. All right, the slide decided to advance by itself. All right, again, put this, here you have 1 minus 1 is 0. No, I'm sorry. 1 minus 1 is 0, and here you have a 0 times a 1, which is 0 plus 0. So you still have an indeterminate form, okay? Now, if you get least common denominators again, here they skip lots of steps. This becomes x minus 1 over x. This becomes a x minus 1. This is already a x minus 1 over x plus log x times log x over x. And then they did away with their denominators. 1 over x up here, 1 over x down here. You wind up with just x minus 1. They skipped an awful lot of steps here. X minus 1 plus x log x. Go back and see how we did. I showed you in a little bit more gory detail. Okay. I'm waiting for the box to subside. Because y'all can't see this x log x down here, can you? Isn't the box obscuring it? Or is it? Oh, too late, you didn't answer. Okay, let's take the limit again. This is a 0, that's a 0, this is a 0. So, yep, you're still. Take L'Hopital's rule again. Okay, derivative of x is 1. Derivative of x is 1 minus 0. because the derivative of 1 is 0. And there, another product rule, x over x, which is 1, plus log x. And in this case will be 0. So your new ratio is this. The limit is x approaches 1 from the positive side, x minus 1 over x minus 1. Oh, I'm sorry, they rewrote it, the whole thing again. No, they didn't. This is the new form. Take L'Hopital's rule again. That becomes a 1. That becomes a 1 minus 1, that's 0, plus derivative of this is a 1. Derivative of that is a 0. That's what I meant to say. Plus x over x, so there's your 1 again, and this is plus log x times 1, which is just log x. So I had said that on the last slide, and here we have it. Take the limit of those. Here you got a 1, here you got a 1, here you got a 1 again, so it's 1 over 1 plus 1 is 2. Here you got a 0. So that gives you your 1/2. Exactly what we got. Okay? Now, it says you can check the reasonableness of this solution by using a table and letting x go closer and closer. Start out something to the right of 1. They chose 2. And they calculated this thing and came up with 0.442. Got closer to 1, like 1.5, they got 0.466. Well, that is getting closer to 1/2. Let's keep going. 1.1, they got 0.492. Again, getting closer to 0.5. And I think you can't see it until this disappears. Let's get closer to 1, like 1.01, you get 0.49917. That's awfully close to 0.5. 1.001, you can't see probably. 1.001, you plug that in. Come on. Here we go. You get 0.499992. 1.0001, 4.99999, that's, 1.00001, you get 0.5, and about as close as you can get to it. Still a digit out there somewhere, probably that would be a point. But anyway, to 5 digits is a half. Anything beyond that, even closer to a half. Okay, that's how they say check the reasonableness. That's a lot of checking to do the reasonableness. I'll take the word for it. It's 1/2. So here's sort of a summary here. The form 0 over 0 for sure. Apply L'Hopital's rule as you see it. Derivative of the numerator, derivative of the denominator. Infinity over infinity. Same. Infinity minus 0, you got to manipulate it before you get it into one of these two forms. Okay? And usually that's deals with fractions and changing the difference of fractions to a rational form. 0 times infinity, again, manipulate and see if you can get something over something. You have to get it in a ratio form. 0 raised to the 0, that's a candidate for a log transform. Do that, but remember to go back and exponentiate at the end. 1 to the infinity. We haven't worked one, I don't recall like that. That would be the same thing. Anytime you have something raised to a power, take a log and get it into a product. And 0, infinity raised to the 0. Again, do a log transform. Those forms have been identified as indeterminate. There are similar forms you should recognize as determinate, okay? If you got the difference of two infinities, at least that has a hope of going to some finite number. If you have a sum of two infinities, no way. That's just going to get bigger and bigger and bigger and bigger. So don't even thought. The limit I don't know. I don't like this. The limit is positive infinity. To me, the limit doesn't exist, okay? It keeps getting bigger. Or if you have minus infinity, no way that's going to be approaching anything finite, so that's going, again, the limit will not exist. Now, 0 to the infinity. Here there's 0 to the 0th power. One of those was going to, okay, nobody came in today. I don't think so. At least there's a chance that could be going to 1 or something else. 0 going to infinity. 0 times 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 0. Just keep multiplying as many times as you want. No chance of it ever being anything but 0. Okay? That limit is 0. How about 0 to the minus infinity? That's 1 over 0 times 1 over 0 times 1 over 0 times 1 over 0. No way that's not going to be not existing, going to positive infinity. Okay? So, those might look like these forms up above, but they are not indeterminate. They call it determinate forms. All right, any questions on that? As a final comment, remember that L'Hopital's rule can be applied only to quotients leading to indeterminate forms. I've said that several times. Either 0 over 0 or infinity over infinity. Either one of those will work. For instance, the application of L'Hopital's rule here is not correct. As x approaches 0, e to the x is 1, x is 0. That's not an indeterminate form. That is a does not exist form. You cannot use L'Hopital's rule here. So don't even try. Okay? It has to be either 0 over 0 or infinity over infinity. A 1 over 0 does not qualify. That limit does not exist. The reason this application is incorrect is that even though the limit of the denominator is 0, the limit of the numerator is not 0. It's 1. And therefore the hypothesis of L'Hopital's rule not satisfied. You can't apply a rule that doesn't meet the requirements. So don't even try. All right. Any questions on that? That is the last slide in section 5.6. Finally, homework exercises here would include any of the odds, either 3 or 5. They're both at calcchat.com. Any of the odds 7 through 13, they're all at CalcChat, 7's at CalcView. Any of the odds 15 to 41, there's a whole bunch of them there. Don't do them all, but do as many as you need to feel comfortable about it. They're all at CalcChat, 29's at CalcView, if you need a fuller description of what's going on. Any of the odds 43 to 61, again, a whole passel of those. You first make sure L'Hopital's rule applies and then try to work it out. They're all at CalcChat, 51's at CalcView. You can explore doing either 63 or 65. That's up to you. They should both be at CalcChat. 67 should be at CalcChat. Any of the odds, 69 to 73 should be at CalcChat. Okay? 75 or 77 should be at CalcChat. Now, you can think about doing 79 or 81. I kind of don't like those, but it's what they were doing at the very end. They've written something in the book that's wrong. So they put big red X's to let you know they're wrong. They want you to figure out where they missed the boat. Okay? What was the incorrect step? Okay? 83 should be at CalcChat. And by the way, those two odds should be at CalcChat. 85 should be at CalcChat. So application problems, 87 and or 89, they should both be at CalcChat. 89 is talking about the gamma function. And that may lead you to a potential paper topic if you're interested in that kind of thing. So I'll let you figure that out. If you want to do the problem, that's even beside the point, okay? Now, extended mean value theorem, we did that. So either 91 or 93 should both be at Calc Chat. There's some true false here. Any of the odds between 95 and 99, you certainly should be able to do those. They should be at Calc Chat. 101 is an area problem. That should be at Calc Chat. 103, continuous function problem. That should be at Calc Chat. 105, let me say this. Excuse me. Any of the odds between 105 and 109, they should be at Calc Chat. They refer to a journal article here. If you're interested in pursuing that, you might be able to find the paper topic. It kind of leads to a proof. So 111 is a proof if you want to do that. If you don't have to. 113 and 115, you could choose either one of those to do. They should all be at Calc Chat. 117 is a Putnam challenge, which usually is quite a challenge. So I'll let you decide whether you're going to do that or not. Okay. Now, let's move on to, let's end 5.6. Any questions on 5.6 before I close out the PowerPoint? Okay. Now my screen sharing stopped, but I'm going to pick up 5.7, which is right here. All right, we should be screen sharing again. We'll start the slide from current slide. And I will also move this taskbar. I don't know if you can see it or not, but it's right in the middle of my PowerPoint. So I'm going to move it down here as much out of the way as I can. Okay. Let's see how many people we have. 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, good deal. Okay. So chapter 5 is still dealing with integration. Well, it won't advance until I click on the screen. Okay. 5.7 is dealing with the natural logarithmic function and integration. Well, it almost feels like we've been dealing with this already, but possibly not in an integration type rule. Let's see what they mean. Objectives here are to use the log rule, okay, which we haven't decided for integration to integrate a rational function. And we'll integrate some trigonometric functions because guess what? They can often be expressed as rational functions. Okay? So what is the log rule for integration? We've studied two different rules for logarithms. The differentiation rule, d by dx of log x, like saying d by d, okay, is 1 over x. Okay? And we're going to use that rule to produce the log rule for integration. So the differentiation rule, d by dx of log u, is u prime over u. We sort of did that a little earlier. That produces an integration rule that the integral of 1 over u, they've left off a du here, okay, should have a du in there, is equal to log u plus c. That's just undoing your differentiation up here. If the derivative of log x is 1 over x, then the integral of 1 over u du should be log u plus c. Remember, when you integrate, you always have to, at least an indefinite integral, you have to add a constant of integration. And those rules are summarized below, and here's what you got. Okay? Let u be a differentiable function of x. Okay? Not showing up here. The integral of 1 over x dx, because this is the derivative of log, the antiderivative of this should be log. But with this exception, you have to put the argument inside absolute values, unless you know for some reason that argument has to be positive, okay? If you don't know that, put them in absolute value bars. And then always add your plus c. Now, on the other hand, if your integral, and remember u is a differentiable function of x, that would be the integral of 1 over u du is simply log absolute value of u plus c. Now, frankly to me, this was ridiculous to list this twice. And here's why. I know why they did it. But look, this is a dummy variable here, okay? So it doesn't matter if it's x, u, stickman, or whatever, it's always going to be the same. So this looks like to me it's one rule, not two rules. Now, I know what they're meaning. What if this is some function of x and this du is a function of dx, but it happens to be exactly your du? I know what they're getting at, but phrasing it this way was rather silly, I thought. Now, they say here because du is u prime dx, the second formula can also be written this way. The integral of u prime over u dx is log absolute value of u. That I'll buy, okay? That, because you see, the u prime dx was your du. This makes more sense, okay? The other is correct, for sure, but it didn't matter what the variable was. This one, now you're using the fact that u is a function of x, and that gives you the log of absolute value of u. Okay. Let me pause a minute. My throat's getting awfully dry. All right. Do y'all need the whiteboard on this one, or is this fairly close to self-evident? Do you need the whiteboard? Here, all you have is an integral of 2 over x dx. Number one, that 2 is not doing anything here. Take it outside the integral. And now you have 2 times the integral of 1 over x dx. And that is simply, tell me somebody. Anybody? It's 2 times log x plus c. Okay? Now, if you say 2 times log x, you could also write that as log of x squared. Okay? And believe it or not, that is also correct. Okay? So let's see how they do it. Yep, 2 times the log of absolute value of x plus c. That's the log rule for integration. And you can take this, remember that this is going in the other direction. If you have a constant times the log of a base, make that the log of the base raised to that power. And guess what this form gives you? The ability to lose the absolute value bars. Because it doesn't matter whether that x is positive or negative. Here, if the x is negative, you have to take absolute value of it. Here, if the x is negative, who cares? When you square it, it becomes positive. You can take the log of any positive number. Okay. You just can't take the log of 0. You can't take the log of a negative number. So this is actually the slightly better way to end that problem. You can lose the absolute value bars. Okay? Does everybody see why? Any questions? Okay? Because x squared cannot be negative, the absolute value notation is unnecessary for that final form of the antiderivative. Okay. Now, if you have any doubt about whether this is correct or not, take a derivative of it. The derivative of log of any function, x squared included, would be 1 over x squared. But because this is a composite function, you then take, by chain rule, the derivative of x squared, which is 2x. So it's 2x over x squared. One of the x's cancels out, and you're left with 2 over x. And that's what you started with, because derivative of c is 0. So sure enough, you go back to 2 over x dx. Okay, any questions on that? Let me pause another minute here, goodness gracious. Hope I'm not getting something. My throat is fairly raw. All right. Log rule for integration. Integrals to which the log rule can be applied often appear in disguised form. They're really tricky. For instance, when a rational function has a numerator of degree greater than or equal to the denominator, you have to apply division, polynomial division, especially if it's a, well, let's just say division. It doesn't have to be polynomial. You have to divide. But when you talk about degree, usually you're implying polynomial degree. Okay, so you have to use division, whether you call it polynomial or not, to reveal a form to which you can do the log rule. And this is shown in example 5. Well, my question is, what happened to examples 2, 3, and 4? They skipped them. That's what happened. So let's us go to our whiteboard. Now, how are we doing on time? Okay. We go until 2:25, so we got plenty of time. Now, I don't think you can see my taskbar. It's right smack messing up the whiteboard. So I'm going to smack it over here and move it out of the way. Okay. May also move this a slight amount this way too. Okay, I think I've got it cleared as much as I can. Let's clear this thing. Nobody needs this one anymore, right? So let's clear that out of the way. Now I've got a big old rectangle here. Please move this window away from the shared application. I can't, but this isn't blocking anything, is it? You can't. I don't have anything written, so you can't tell. But other people in other classes have said it didn't. So let's come over here and do example 2. Okay, example 2 is the integral 1 over 4x minus 1 okay, times dx. Now, yeah, all right. Now, you don't have to do it this way, but I find it far easier to do this way than trying to see through the crystal ball and see what the answer should be. I'm a little surprised because sometimes the book likes to see through a crystal ball, and you're supposed to be able to see what they see. Okay? Here we have a variable in the denominator, which you know I don't like. But it's not something you can just apply a exponential thing to and get rid of it, because it's not just a variable, it's a polynomial. Okay. So this looks like a great candidate for a U substitution. So what's the most complicated thing here is the fact you got something in the variable in the denominator. Okay. So let's take that denominator. That's the simplest part of that complicating issue, that you have variable in the denominator. Let's let that denominator be your U. So let U equal that denominator. That's 4x minus 1. Sorry about the writing. Okay, there's your U substitution. what always follows the u substitution? A then. And that then almost always means take the derivative of u, at least the differential of u. Du, sorry, it's running together, is equal to, and someone tell me what du is. If u is 4x minus 1, what's du? Derivative of 4x is 4 times, and you're writing in differential form, dx. Because derivative of minus 1 is 0. All right, now, what does that suggest to you? Up here you have a dx, you don't have a 4dx. So to make this a 4dx, to make it just a plain dx, you have to divide away your 4. But if you divide on this side, you also have to divide on this side. Divide both sides by 4. Now you have just a dx here, which is all you have up here. So let's rewrite this integral. But now it won't be an integral in x, it'll be an integral in u. Okay? Well, what you hit here first is 1 over, and what is this in terms of u? Well, that's exactly what your u is. 4x minus 1 is u. So it's 1 over u, and then you have your dx. What is your dx? du over 4. So I'm going to put the du in here where it's convenient to put. It has to be inside the integral, but because the 1 over 4 is just a constant, I can move it outside here. Okay, that's a 1/4. Oh boy, my hands are getting crampy from doing all this. All right, I think we can do this integration or anti-differentiation anyway. The 1/4 comes along with it. Don't forget it. It's not to be thrown away. That's a 1/4. Now, what's the antiderivative of 1 over u du? Please, someone tell me. Antiderivative of 1 over u du from your log rule is log of the absolute value of u. Don't forget to put that in there. And then you can add your plus c, your constant of integration. Now, later we'll probably play around with naming that constant something other than c. Like, since you have a log here, you can make it log c. That's still a constant, okay? There's no reason to at this point, but just looking ahead, sometimes that will make things a little more convenient, okay? Now, you're not through though. Because your problem initiated with x's, you'd need to get back to your x's. So that's the same as 1/4. And you go to that first line again, the log of, and unfortunately here there's no reason that you can eliminate the absolute value, so you have to keep them. The u is 4x minus 1. Plus c. All right, that's the answer. Let's see what they got in the book. 1/4, the log of absolute value of 4x minus 1 plus c. Now, for some reason, they do put capital C's there. I don't care which c it is. Some of mine look like lowercase c, some look like capital C's. I'm having trouble writing periods, so there's nothing special about what size the c is. Okay. Now, let me bring my book in my lap so I can see example 3 better. They left that one out as well. Any questions on example 2 before I erase it? Any? Please speak now. Okay. Let's clear the drawing and let's go to example 3. This time it's a little more practical. It's not just saying find an integral. It's saying find an area under the region bounded by the graph of, so here's the graph, y is equal to x over x squared plus 1, x over x squared plus 1, okay? The x-axis, so that's going to be the lower part. We've figured this function may or may not be positive. We're figuring it will be positive. We'll see. The x-axis and the line x equal 3, okay? I'm not going to put x-axis, but I want to put down x equal 3. Okay. Now, I really don't like the way they worded that. They should have said between x equals 0 and x equals 3. Now, sure enough, at x equals 0, you're at 0, okay? But x could be negative here. But then you're in negative territory for y. So we usually don't think of areas when they're negative. So they probably should have said between x equals 0 and x equals 3. That's what they're doing the calculation on. So basically that tells you you're integrating, finding an area, just like finding the slope of a tangent line means you differentiate. Finding an area under a curve, that means you integrate. So this means you're looking for the integral, and like I said, it's now, they didn't say it, but they imply it, going from 0 to 3. So that's going to make it a definite integral of this integrand, x over x squared plus 1 dx. And if it helps you to remember, you've broken that area into narrow little strips. Think of them as delta x's. This is the height of the strip going to the x-axis, so minus 0. That would be fine. Y is equal to this to y is equal to 0. And you're doing this everywhere from x equals 0 to x equals 3. Take the limit of that. As the delta x's go closer and closer to 0, you get dx's, okay? And that summation that you were having becomes an integral from 0 to 3. Definite integral, okay? So there's the problem. How would you propose to solve it? Again, it's one of those situations I don't really care for. What is it that bugs me about it? You have the variable down here in the denominator. And most of the time, I don't care for that, okay? Because it's hard to deal with things down there. So, since it's down there, let's use that denominator as our u. Let u equal x squared plus 1. Oh my goodness gracious. I don't know what to drink. Okay. Always after you make a u substitution, the next line is then what? Take the derivative. You need the d part. So du, or more precisely, take a differential. Du, anyone tell me what that is? Derivative of x squared is?
2x.
2x dx. Differential, you need that dx on this side. Very good. All right. Now, let's take a look at what we've got. Up here we have an x dx. Down here we've got a 2x dx. Doesn't match, so to make it match, we'll divide down here by 2. But if you divide that side by 2, you must also divide this side by 2. Okay? This wipes out the 2's here and here. Okay? So what we have now, the integral, and right now I'm just going to leave the integral sign naked for a bit. What we have, the x dx is simply du. Okay? And down in the denominator, we have a 1 over x squared plus 1. Well, x squared plus 1 is u. So it's du over u. And the part I left out, the limits of integration, this is where we go back and use this line. Because this represents the limits for x, what we want here are limits for u. So since we know the relationship between x and u, we plug in x equals 0. That would be 0 squared plus 1. U would be equal to 1. Up here for 3, x equals 3, plug that in here. 3 squared, 9 plus 1 is 10. So but the u is going from 1 to 10 when the x goes from 0 to 3. Okay? Now we can do our integration, anti-differentiation, whatever you want to call it. Goodness, my eyes are dry. Sorry about this, folks. I know I'm straining them by staring at the screen so hard, but that's how I write. Okay. What's the antiderivative of du over u? Please tell me you know. What we've been doing, the log rule. That's log of u. Integral of 1 over x dx, okay, that's log x. 1 over u du, that's log u. Only you have to put absolute value bars around the u, because you can't take the log of a negative number. Can't take the log of 0 either, okay? But the good news here is, look at this. U is staying between 1 and 10. So guess what, folks? You don't need the absolute value bars. And I've written them, and the eraser is not picking up anymore. So forget I put the absolute value bars there. Because you see here, the u is staying between 1 and 10. Okay? But you do need, oh no you don't. Because this is a definite integral, you don't need your plus c either. But what you do need is to evaluate it. Okay, let's just evaluate it from here. This is when u is going from 1 to 10. That's why we changed the limits so we could evaluate at this point. Okay. What is this equal to then? Log of 10, you don't need the absolute value bars. Log of 10, if I could get the pen to move pen, there we go. Log of 10 minus log of 1. That's the fundamental theorem of calculus, right? But log of 10 is some number. You can punch it in on a calculator if you want to. Since we Southerners are so violent, we punch things, but you know, log 10. But I think you should be able to tell me what log 1 is. Anybody? Anybody? 0. So the answer for this is simply log 10. The area under that curve is log 10. And, oh, wait, you let me do that, didn't you? This du was du over 2, so it's 1/2 of log 10. You let me do that. The du, the x dx became 1/2 du. Bring the 1/2 on the outside. So this will be a 1/2 here. And a 1/2 here too. Now, if you want to be really bizarre about it, you could say that's the log of the square root of 10. But guess what? It's just as easy to calculate the log, 1/2 the log of 10. So pull out your handy dandy calculator, see what you get. Not that it's important in this course. This is more theoretical, sort of. Okay, gonna have to turn it sideways to get. I've got my phone. It's 1/2 the log of 10, so that's going to be 0.5 times, and on my phone calculator I have to enter the 10 first, and then press the ln key, and then press equal. And 1/2 of that is 1.151. Yeah, that's what they got. I would have said 1.1513, but they stopped it earlier than that. No indication of significant digits there, so. All right. I didn't write that down, but it's in the book. Okay, I'm pretty sure they also skipped example 4. Any questions on example 3 before we leave example 3? All right. I'm going to clear it, and let's move on to example 4. Example 4 has 4 parts to it, okay? So let's do the A part for example 4. We may be here for a while. The antiderivative of, or integral of, 3x squared plus 1 divided by x cubed plus x I'm pretty sure that's followed by dx. Ugly looking D, but it's a manage. Okay. How do we do that one? What would be your approach? How would you start? What is messy about it? Variables and the denominator. You can tell I don't like those. Okay? So that's a good place for a U substitution. Now, time out for a moment. We've read the descriptor that leads to example 5. I probably shouldn't have done that until we did these examples, but I wasn't sure it was going that way. But here's something you need to do. When you have a rational expression in your integrand, if that degree of the numerator is greater than or even equal to the degree of the denominator, divide first, then integrate. Here the degree is 2, this degree is 3, the numerator is lesser degree than the denominator, proceed. Okay? If it was greater than or equal to, divide first, then proceed. Okay? That's an ugly little E. Let U equal that's a terrible equal sign. There we go. The denominator, which is x cubed. Goodness, my writing's getting bad. Maybe I need to take a little bit of a break just to give my fingers a rest. I could use a little bit of a bladder break too. So let's see if we can get this one followed. What's the next line that always follows your let sign? Not talking about tennis. Thin line. It's not a thin line, but a thin line. Then, and what does the then always start off with? du is equal to what? Take the derivative of u. What do you get?
3x squared plus
3x squared. I heard that part. What next?
plus 1.
Plus 1. Excellent. And then what part? Remember, you're taking the differential of both sides, so you need over here your dx. Okay? du dx. Okay? Has to have a d on both sides of the equation. Now, if you had written it, du dx is equal to 3x squared plus 1, that would have been okay, but that's not how you want it to look. You want the dx in there. You want it in differential form. And guess what we've got now? There's your numerator right there. There's your dx. We don't have to do a thing to it. No reason to divide by 3 or do anything else. Leave it alone. That is your du. So this integral, and it's an indefinite integral, just goes directly to being du, that's that expression there, over u. Okay, I'm sorry, I got to thinking about something else, wondering if I needed to, no, I think what I was thinking, where are my limits? There weren't any limits on this one. This is indefinite. Okay. We've only got, well, a little less than an hour to go, but I think I'm going to need the bladder break. So I hate to do it in the middle of the problem, but let's stop because it's getting uncomfortable. So let's take a quick break. I'm going to pause my recorder. Remind me to turn that on when we come back. It's just too much, especially right after lunch. Okay. What we've got here, the du was your 3x squared plus 1 dx, which is exactly what we've got here. Your u was x cubed plus x, which is exactly what here. Simply the integral, antiderivative integral of du over u. Someone tell me what that is. The log of the absolute value of u. Okay? Plus c. But we didn't start our problem with u's. We need to get back to our x's. So that would be the log of, and this time we do need the absolute value bars. Absolute value of x cubed, because u is x cubed plus x, plus c. Okay. Now, why do we need the absolute value bars? What if x was negative? If x is negative, x cubed is also negative. And a negative plus a negative is really negative. And you cannot take the derivative of the log of a negative number. Now, the other thing I mentioned earlier is that sometimes, in some situations, you don't want the c to be just a plain c. In fact, in this case, if you'd had your c to be log c, which is still just a constant, doesn't matter how you express it, then the sum of two logs is the log of their product, and you could have called that the log of, if this had been a log c here, then this would have been the log of c times the absolute value of x cubed plus x. And in some situations and applications, that's a more convenient way to write it. In this form, there's no reason to do that. So leave it alone, that's fine. If you look in the book, that's exactly what they get. So there's the A part of example 4. I think I'll clear the screen unless there's questions. Any questions on oh, yeah, I'm afraid I forgot to start the recording back, but I did. So let's clear the drawings and go to the B part. The B part is the integral, whoa, that's an ugly integral, of secant squared x over tangent x dx. I think I could write faster than this, but I just don't seem to be able to pick up my speed. Now, don't be fooled. When I ask this question, what is the most complicated issue going on in this problem? You might look at the exponents and say, well, the numerator is more complicated than the denominator. And in one sense, it sort of is because it's squared with the denominator to the first power. But that's still a denominator. The denominator is the most complicated part. So let that be your u. Let u be that denominator. Most of the time, that's going to be your go-to. I can't say every time, but that most of the time it will be. And that's just simply tan x. Tangent of x. Almost wrote that as tax, but it's tangent x. And what always is the next line? Your then line. After your let line is then your then line. Then, and what is that then line? Take the differential of your let line. du is equal to, and what is the derivative of tangent? I think we've hit it once already today. Anyone know? Derivative of tangent is, believe it or not, secant squared. They were very good to you, weren't they? But because it's differential, secant squared x dx, written in differential form. And this secant squared x dx is precisely your numerator, and that's the du then is your numerator, and your denominator is your u. So this is simply, absolutely, the integral of du going from x's to u, du over u. Ooh, that's an ugly u. And what is that? That is the log of u. Antiderivative of 1 over u du is log u. Plus c, of course, and plus something else I didn't write, the absolute value bars around the u. Because there's nothing here. U is tangent x. Tangent can be negative. It's not guaranteed to be positive. Not for all values of x. Some values of x it is, some it's not. So you need the absolute value bars. But because your problem was given to you in x's, change back to give your answer in x's. That's going to be the log, the natural log of, again, absolute value. And what was your u? Tan x. Absolute value plus c. Now, there is absolutely no reason to even try to think of another way to express that constant because there aren't any rules for, oh, yeah, I guess you could. Yeah, you could say the log of c, and then the sum of two logs is the product of their logs, okay? The log of their products, I'm sorry, I said it backwards. So that could be written as, if you had called the constant log c, then you could call your final answer log of c times tangent x. Okay, but there's no, yeah. But there's no real reason to do that. So log tangent x plus c. Well, for some reason, I feel like I've got to sneeze. And I'm sorry. Okay, I hope y'all are all awake now. Okay, let's do the C part. Any reason not to clear? Any questions? Whoops, that's not what I want to do. Okay, that's what I want to do. Okay, the C part. The antiderivative of, or integral of, x plus 1, here's your numerator, over x squared plus 2x. Okay, that's times dx. Okay, what would be your approach to this one? How would you begin? What's the most complicated looking part of that issue? Again, most of the time it's going to be the denominator. Thing to watch out for though, make sure the numerator is lower degree than the denominator. If that had been an x squared up there, nope, divide first. If it had been an x cubed or anything higher, divide first. But with this is x to the first, that's x to the second, you're fine. So, again, first good guess would be a u substitution. Starting with the let term, let u equal, this is your u substitution here, that denominator, x squared plus 2x. Always following the let line is a then line. Then you write the previous thing in differential form. du, it's an ugly d, is equal to, someone tell me, what's the derivative of x squared?
2x.
2x. And then the second part?
Plus 2.
Plus 2. And then the third part?
Dx.
dx. Excellent. Okay. Now in this case, I kind of like to put a parenthesis around it so you don't think that dx just goes with the 2. Okay. Now the question is this what you got up here? No, not quite. Now why is that happening? Is someone else able to write on my screen? I think maybe someone is and didn't realize you're able to. But I don't think I can erase because my eraser's not working. If you can erase, go and get those out of there. But if not, they're not hurting anything. Let's take this one more step, because you see you can factor a 2 out of both of those terms. So do it. Factor out the common factor of 2, and what are you left with? X plus 1 dx. Now, that's what du is. Up here, you do have an x plus 1 dx, not a 2, so divide away the 2 here. But if you divide on the right, you must divide on the left as well. And that then leads to your new representation of this integral, not in terms of x's anymore, but in terms of your u, the x plus 1 dx. Oops, I didn't wipe them out. There, they're wiped out now. Okay, x plus 1 dx is du over 2. So this is where I put my 1/2 out front, the over 2 out here, and then do my integral. And then this would be my du from that previously du over 2. We got the 2 on the outside, this on the inside, and your denominator is merely u. And what does that integral become? Don't forget your 1/2, that's important. What's the antiderivative of du over u? I don't know why I can't write now all of a sudden. Log u. Except, I need to put my absolute value bars there. Probably not a bad idea to put a parentheses in front. You don't have to, but it would be a little more precise because it's 1/2 of all this, and that is log u plus c. But it really doesn't matter whether the parentheses are there or not, because c is a constant and c over 2 is a constant. So it doesn't really matter, okay? If you put it in parentheses, it would indicate you have a c over 2, which is a fine answer too, but it doesn't matter. Now, the one last step is to get back to our x's. So that'd be 1/2 the natural log of absolute value of x squared plus 2x. If I could get my pen to write. Okay. That's supposed to be absolute value bar, not parentheses. Okay, plus c. Whew, goodness gracious. I feel like I've been run over by a truck, though I don't know what that really feels like. So 1/2 the log of absolute value of x squared plus 2x plus c. Good answer. Any questions on that? Now let's see if my clearing here is going to clear the green lines. Let's see. Yes, it did. All right. Hold on, folks. Let's do the D part. Well, this almost seems like a step back. But let's see if you remember the step back. This is an integral of 1 over 3x plus 2 dx. Any suggestions on what I do first? You absolutely have to have it this way, but I find it easier to do it. Do your U substitution. And what's the most complicated part? Of course, it's the denominator. Okay, and the innermost part, the only part of that is your denominator. Sorry. Let U equal your denominator. That's what it's been for the last several times. 3x plus 2. Then, always follow the let by then. And you write the differential form here. du is equal to, you tell me. Oh, that's ugly. 3 dx, because the derivative of 3x is 3 times dx. Sorry, the d went wherever it wanted to. It wasn't where I was trying to get it to go. And my eraser's not working, so I can't do anything about it. Well, up here we have a dx. I sure don't see a 3dx. So let's get this down to a dx by dividing both sides by 3. And then when we come over here to express this integral not in x's, not in x's, but in u's, first that dx is going to be, oh, I forgot to cross these out. Okay, that's a pretty ugly crossing out. Got rid of the 3's there one way or another. So your dx is now du over 3, so pull that 1/3 out of the integral. And then write that integral as du, because it was a 1/3 du, but we put the 1/3 out there, over u. And of course we know what that integral becomes. 1/3 of the log, goodness, this is hard, of absolute value of u. And of course we have a plus c coming at the end. Okay, now's the step. We went here to get from x's to u's. Now here we go from u's to x's. That's equivalent to 1/3 the natural log of the absolute value of, and your u was 3x plus 2. All right, plus c. Okay, so there is our final answer. And in the book, you've got it, 1/3 log of absolute value 3x plus 2 plus c. All right. Now, they're now mentioning what I was saying earlier, that you could then write this as the log of this thing here raised to the 1/3 power, which would be the same or equivalent to saying the log of the cube root of this thing here. That would be okay too. You have to keep the absolute value bars somewhere there, because cube roots can be negative as well. Square roots, generally not, okay? But cube roots, yes, okay? So in this case, you'd have to keep the absolute value bars. Now, the question is, do you put the cube root inside the absolute value bars or outside the absolute value bars? It doesn't matter, okay? Either way. And they give you that in the book as well. Okay. Now I think we're ready to go back to the slide set, though I have a feeling we'll be right back here at our whiteboard soon. But let's go back to current slide. For some reason, the slide always goes back. Now, this is what I should have waited to read until after we did example 4. Integrals to which the log rule can be applied often appear in disguised form. Silly way to phrase it, but it's okay. For instance, when a rational function has a numerator of degree greater than or equal to that of the denominator, division rule may reveal a form to which you can apply the log rule that it didn't look like you could before. And that's what example 5 is showing. And here comes example 5. Find the definite integral of this. Well, if you look at that, say, well, that's going to be my u, then the du is 2x dx. But you don't have a 2x dx here. So you say, wait a minute, wait, I can't do this. Well, no, you can't do it at all because this is what they call an improper rational expression. The degree of the numerator is equal to the degree of the denominator, and anytime that's the case, you start by dividing. So let's go back to our whiteboard. I told you it wouldn't be long. Okay. All right, to clear the previous one. I hope there were no questions on it, but if so, I'll ask now. None? Let's go back. Where's example 5? I'm going to write it down again. The integral of x squared plus x plus 1 over the integral of x squared plus 1. Not the integral, but x squared plus 1. That's a 2. It doesn't look like 1. But the pen just wouldn't write any further. Let me see if I can get it to now. There, it's writing a little more. Okay, that's a 2 now. I can't erase, so hang up that concept. Okay, and then your dx. Now, as tempting as it might seem, don't try to make a u substitution yet. What we do, we take that integrand, pull it out here, and make it a division problem. Okay? Because that's the dividing line. That's what the horizontal line is. Now I'm going to write it this way, hopefully to make it a little clearer. Okay? It may not. You may not like this at all, but I can remember sometime in early years, maybe grammar school even, when they were teaching, no, it had to have been more like late junior high or high school, early high school. X squared plus x plus 1 okay. Sure hope I wrote the problem right. Yeah, I did. Divided by x squared plus 1 okay. Now, the reason I wrote it this way, I remember something like this from back in my youth or childhood. Bring down your division sign and put the numerator in here. X squared plus x plus 1. Now, you got one other thing I should have done and I neglected. In both the numerator, which is down here inside the house now, the dividend, be sure all your terms are covered. You really should do that for your divisor as well. So I'm going to try to squeeze in here a plus 0x. Now you probably can't even read that, but I put it in there because you really need to have every term accounted for. Now, how do you do long division? Hopefully you remember. Start at the left. All other operations, we start at the right and work our way to the left. Division, we start at the left and work our way to the right. So start at the left, x squared into x squared. That'll go one time. Now, I've seen some books, and I think this author is one of them, who likes to move this over above the one here. You can if you want to. Since I'm doing x squared into x squared, I like to put it over the x squared. But you don't have to. You can put it over the number of the same degree. I don't care. Then, once you divide, you multiply. 1 times x squared is x squared. And this is why it's important to put that extra term there. 1 times 0x is 0x plus 0x. Okay? Now, what we do now is, oh wait, I forgot. 1 times 1 is 1. So you have a plus 1 here too. Okay. Now, what I like to do, usually when you're doing long division, divide first, then multiply, then subtract. And in this problem, subtraction is a perfectly great thing to do. But in some, when you have different signs in here, SIGN signs, sometimes subtracting sign numbers makes people cause errors. So what I like to do is rather than rather than subtracting, change signs and add. So I'm going to make that's a minus. Oh, I can't do it here. I'm used to being able to erase. Make that a minus and make this a minus and then add. These two add to 0. This adds to just an x and this adds to a 0 as well, because that's a plus x here, a minus x there, that adds a 0. So if you can't erase, it may be not a good idea to do it because it looks confusing. Well, what does this give you? This gives you a remainder. Well, how do you write a remainder? And now, how do you know it's a remainder? Because its degree is less than the degree of the divisor. That guarantees it's a remainder. How do we write it? That's plus x over your divisor, x squared, and now you don't need the extra term there, x squared plus 1. Okay, I can't get my pencil to move. There it goes. Plus 1. Goodness gracious. I can't believe how dry I get. Okay, now remember, this was your entire integrand. So now this is your entire integrand. This thing here, we operated on it, and we got this to be our integrand. We divided this into that. You got this as a quotient with that remainder over this, so that is your answer. So we go back to our integral and write in what we've got. We've got a 1, and if you don't mind, I'm going to break this into pieces. 1 dx plus the integral of this part, x over x squared plus 1 dx. Now what I just did, I did it in one step because I just didn't want to write any more than my fingers had to. Okay, we broke this integral here because this was a sum of two pieces here into 1 dx plus the remainder over divisor dx, the integral. Broke that into two integrals. Now, please tell me someone can do this one. What's the antiderivative of dx? X. Because when that derivative of x, you get 1 dx, right? Yeah, that's it. Okay, plus. Now, in this part of it, it looks like a u substitution. So I'm going to do the u substitution off here to the side rather than underneath because I didn't plan ahead. So let your u be, guess what? That denominator, x squared plus 1. That's supposed to be a 2. It's not coming out as a 2. X squared plus 1. That denominator. And follow the let by then. Du, differential, du, yeah, it's getting hard, folks, is equal to derivative of x squared is 2x. Derivative of 1 is 0, so you then have your dx. Remember, you write in differential form, you need a d on both sides. D on the left, D on the right, stand up, sit down, like that. Okay, now, in this integral, we have an x dx. Over here, we have a 2x dx. We don't want 2, we only want 1, so we're going to divide out a 2. But if you divide that side by 2, also divide this side by 2. Here, these 2's go out. They've been dating, okay? And now you got x dx, which is exactly what you got here. So this becomes, here we have a du over 2, so let's take the 1/2 on the outside. I almost forgot to, but I did forget to on the previous problem. The integral of du is all that's left here. That's your du in the numerator. And in your denominator, you've got merely your u. And that hopefully should look very familiar to you now. This would be x plus 1/2. If I could write 1/2. And the integral of u du is, it's an ugly 1/2, okay, log u. But what's wrong with this picture? You start off with an x and wind up with a log. And by the way, that's the absolute value of log 2. And you're going to have a plus c, which I haven't written down yet. But what we want to do is plug this u into this expression here, x squared plus 1, and for that u. And the good news here is you get an x here plus, and if you can remember, that is a 1/2. The log, natural log of, and plug in what the u is, and the u is x squared plus 1. Guess what? X squared plus 1 is never, ever, ever negative. Because x squared, the least it could be would be a 0, and you add 1 to it, and it's going to be 1. So it's always positive. Any other x, going to be positive when you square it. Okay? So that you don't need the absolute value bars anymore. Put parentheses, x squared plus 1. And then a plus c. Now, sure enough, you could have written that as x plus the log of the square root of x squared plus 1, which would be a perfectly good way to write it 2 plus c. There's no reason to do it. I don't think they do it. They don't. They leave it just like that. Okay? Now, will this give us the same thing if you take a derivative of it? If you were to try, take a derivative of this, you get 1 plus 1/2, 1 over x squared plus 1 times the 2x up here. The 2's cancel out. So 1 plus, 1 plus, oh boy, x over x squared plus 1, and then write that as a common, with common denominators and combine them together, you're going to get the same thing. Okay, and derivative of c, of course, is 0. Okay, that was example 5. So let's go back and see how they do. Was that example 5? Yeah, okay. And by the way, I didn't say it before. This is 5-7. I don't know why it went black on me. Okay. All right. Remind me, we only got 11 minutes, so don't let me run over because I got another class 5 minutes after this one. All right, so let's see how we go. But find the indefinite integral and begin by using long division, which is exactly what we did. Okay, remember your divisor is the thing in the denominator and the dividend is the thing on top. And that's why I like to pull down and put under so you never confuse them. Okay? Now, they didn't put in the plus 0x. I think it's a good idea to, but they didn't. They just did x squared into x squared was 1. I told you he always puts this over here on this. Then you multiply 1 times x squared is x squared, and 1 times 1 is 1. Line those up too. Then subtract, these two go out, those two go out, but this will be an x. So your integrand here becomes this, 1 plus x over x squared plus 1. Now you write that as your integrand. Now they put that extra step in there. They weren't writing with their fingers, so they had a typesetter do this on a computer, so it was far easier for them. And then you can either split that into 2 integrals or just integrate as is. I think it's easier to do 2 integrals, which is what they do. The integral of 1 dx is just the antiderivative of dx plus, and here they jumped the gun. They showed the step of breaking into integrals. What they didn't show is that they wanted a 2x up here, so they put a 1/2 out front, which is exactly fine, but it's not the way we had been doing it, but it is a perfectly correct way. And this then would be x from this one, and then it would be 1/2, and this, because you see the numerator is the division, is the derivative of the denominator, that would be this log of x squared plus 1. And I'll notice they did not do a u substitution. They just proceeded this way. It's fine to do that if you see it. If you don't see it, u substitution will take care of it for you. Okay? But by avoiding the u substitution, you avoid a lot of steps. So you paid your money, you take your choice which way you want to write these. Add, I think, it says check that result by differentiating to obtain the original integrand. If we had time, we'd do that. We don't. Let's move on. Now, before you get the guidelines for integration, there's example 6. And let's take a look at 6. So So I'm going to go back one slide here and do my 6 here on the whiteboard. Now, we may not have room to finish it, but let's at least get started on it. We may surprise ourselves and can do it. Here's the indefinite integral. They're sort of sneaking something up on you here. Let's see what it is. The integral of 2x over x plus 1 squared. Okay, I'm trying to get the pen to move and it won't do it. Okay, dx. Well, this is a slightly different kind of problem. Now, there are a couple of ways you can do this, okay? And one way that might come to mind would be, well, let's expand that binomial and make it x squared plus 2x plus 1. And then let that be our u. That may seem like a logical, and it is a reasonable way to do it, but you will run into a difficulty that way. Let's do our u substitution, okay? Remember, the most complicated thing here is your denominator, but the innermost part of that complicated denominator is this x plus 1. So that should be your u substitution. Now this is where we run into difficulties, because this is a little bit different kind of problem. Let u equal x plus 1. Okay, then du, like we always do, is equal to dx. Okay, here's where the complication arises. Look at what we've got up here. We have a 2x dx. All we want is a dx. Okay? Now, we can deal with the 2 part. Let's deal with it. Okay? Let's just take that out of the integral. That's okay. That's a very legitimate step. But now we have x over x plus 1 squared dx. Okay, we're trying to do a u substitution here, and that's fine for the denominator. That's just what we want to happen. However, the numerator is a problem, because all we have here is a dx. Here we have an x dx. But look at here. You can get an x out of here. This implies, if you solve for x, you get x equals u minus 1. Do you see that? Sort of a trick here, but it is legal. Subtract 1 from both sides, you get x equal u minus 1. So now your u transformation, substitution, becomes this. 2 times the integral of, and instead of x, we write in u minus 1, okay, over u squared, right? Because the u was x plus 1 squared, okay? Okay. And then you have your du is merely, your dx is your du. What was it? Yeah. Now, you need another transformation here. Let's see if we can do it. We've used u, so this time let it v equal u squared. Then, I'm sort of in a hurry, so I'm not asking you to come up with it. dv, writing in differential form, is equal to, guess what? 2 u du. And guess what you do? Just bring that 2 back in here, and you have a 2u du. But here we have another problem, folks. That just dealt with the u squared. We still got a minus 1. Well, this is going to be fine for that, so what we do is actually go over here and do this. That's going to be the integral of 2u over u squared du. We've just worked that one out almost, okay? And then we have a minus 2, because that 2 is still on the outside here, of the integral of 1 over u squared. I don't want to write it that way. I'm going to write that as u to the minus 2 du. And guess what? We can do that integral too. This one here is exactly what we set up to do here, and that's going to be the integral of, no, I'm sorry. Yeah, I'm in a hurry and I'm making a mistake. That's going to be, yeah, it is. I'm sorry. I should have had the integral sign in there, but I can't erase it now. Sorry. Okay. That's the integral of dv over v, and my time is up, minus, and I'll do this integral here, 2, what's the antiderivative of u to the minus 2? That would be u to the minus 1 over a minus 1, so that's going to do that, change the sign there, and then we'll have 1 big old plus c out here that covers both of the integrals, okay? And this is going to be log v. Then go back and substitute what v is. V is u squared, so that's log of u squared. You don't need absolute value bars there. Then you go back and see, well, what is u? It's x plus 1, so it's log of x plus 1 squared plus 2 times x plus 1, 2 over x plus 1, basically, okay, plus c. And that is your answer to number 6. 2 times log of x plus 1 okay, plus 2 over x plus 1 plus c. Now they got a 2 there. I don't sure that they're justified in having. But anyway, you can follow up on that. We got to end it there. We've run out of time. I've got to find my pencil. Okay, we'll begin next time with the guidelines for integration, which is the next slide. Any questions? Sorry we ran out of time, but we did. Sorry. All right, I'm going to clear the drawing. Any questions? I'm going to get out of this, out of the whiteboard. And any questions? I'm going to end this meeting. So that means, wait, before I end it, I forgot to give you your homework assignments. Okay, I knew y'all were complaining about something. Homework assignments here, any of the odds 5 through 27. They're all at Calc Chat, 9's at Calc View. 29 or 31, both at Calc Chat, 29's at Calc View. Let me see, how far do we get? Guidelines for integration. I think that might be about it. Let's just do 5 through 27. Any of the odds 5 through 27. All at Calc Chat, 9's at Calc View. We'll hold off and do the others later. Okay? Good deal. Sorry, almost forgot the homework. I knew y'all didn't want to go into a weekend with no homework. So there you got some more. Have a good weekend. We will see you on next Monday, right? Good deal. No questions? Bye-bye. Okay, I've got 2 minutes before my next class.